This Explain Everything video is intended as an instructional resource to help teachers more effectively conduct the lesson as described in the unit teacher notes. The same acceptable use policy restrictions apply to this video as they do to the rest of the curricular materials made available by AMTA. In Units 6 through 9, the Thomson model of the atom has met our needs for the concepts addressed in these units. Now that we're ready to understand the role electrons play in chemical bonding, we need to set the stage for the Bohr model of the atom. In modeling instruction, one doesn't modify or abandon an existing model unless there are phenomena the model doesn't adequately explain. This guided demonstration on thermal energy and radiation helps to provide the rationale for why the Bohr model is needed. The optimal apparatus for performing the demonstration on thermal energy and radiation is an incandescent display bulb plugged into a variable power supply, or variac. This piece of equipment can sometimes be found in the physics stockroom at your high school. Here the display bulb is in an outlet to socket light plug that is plugged into an extension cord connected to the variac. The bulb filament is barely glowing because the voltage supplied to it was dialed down to 5 volts. Unfortunately, variacs are not always available and they're quite expensive. A relatively inexpensive alternative can be made using the following materials: a 16-inch piece of 1x6 dimensional wood or 3/4 inch plywood, 2 bulb bases, a switch cover plate, a rotary dimmer switch, a junction box, and a 6-foot extension cord. These can be found at Lowe's or Home Depot for under $20. So that the lamp bases can lie flat on the board, you need to cut a groove in the board for the wires to fit under them. This can be done by drilling adjacent circles 1/4 inch deep using a Forstner bit or by using a router and straight bit. Attach the junction box to the board using screws or nails depending on the model you got. Make sure that the opened end of the junction box overhangs the board by about 1/8 of an inch so that when you place the cover plate on the box, it will fit over the edge of the board. Clip off the outlet end from the extension cord as it is not needed. Punch out 2 of the tabs in the back of the junction box. Insert the free end of the extension cord into one hole of the junction box and then back out through the other end. Make sure there's enough free wire to be able to reach the base that's farthest from the junction box and to leave a loop so that you'll be able to wire in the switch. Next, using a utility knife, separate the wires of the extension cord, strip the ends, and attach to the bottom of the bulb bases. You'll need about a 6-inch piece of wire stripped at both ends to connect the bulb bases. Use 1-inch drywall screws or panhead screws to attach the bases to the board. Next, cut the hot wire, that's the one connected to the wide prong on the plug end, and strip back the ends of the wire. Connect the wires of the dimmer switch to the free ends of the extension cord with the wire nuts provided with the kit. Then tuck the wires back into the junction box. Attach the switch to the junction box, then attach the cover plate to the switch. The stem of the dimmer switch pokes through the slot on the cover plate so you can attach the knob later. The optimal bulb combination for this apparatus would be a 100-watt clear round incandescent bulb and a 40-watt tubular incandescent display bulb. Since it's not easy to find 100-watt incandescent bulbs with visible filaments, a halogen bulb was used instead. The 40-watt display bulb acts like a resistor, reducing the current through the 100-watt bulb so that the filament barely glows. Use a paper towel roll or something opaque to block the light from the display bulb. This allows you to focus your attention on the filament in the 100-watt bulb. Whether you use the Variac and display bulb or the homemade apparatus described in this video, the object of the demonstration is to examine the light emitted by the filament at various temperatures. At the lowest energy supplied to the bulb, the filament barely glows and the light is reddish in color. To answer questions 2 and 3, students need to note that as more energy is supplied to the filament and it gets hotter, not only does the intensity of light increase, but the color of the light also changes, from red to orange to yellow to white. To more closely analyze the light emitted by the filament, a spectrophotometer is needed. Here, a Vernier Go Direct SpectroVis Plus with optional optical fiber is used. Light from the filament is directed to the SpectroVis, and the spectroanalysis software breaks the light into its component colors. This is the spectrum when the filament is barely glowing red. Note that the graph is a plot of intensity versus wavelength of light in nanometers. The second trace in this graph is the spectrum when more energy is supplied to the filament and it glows orange. Here, the third trace, when even more energy is supplied to the filament, is shown. Note that the intensity increases, but also that more of the output is shifted to the shorter wavelengths. When the filament gets even hotter, the light emitted appears white to our eyes. The graph reveals that light from the blue end to the red end of the visible spectrum is emitted, although the output is stronger toward the red end of the spectrum. Students now have enough information to answer questions 3 and 4 on the worksheet. Make the point that heating the filament produced some change in the structure of the matter that was responsible for the light emitted. What structural change could have occurred? The filament, an atomic solid, was still a solid. Certainly the atoms were moving around faster. Perhaps some change was occurring inside the atoms. Could movement of electrons be involved in some way? Here, the incandescent display bulb has been replaced by a compact fluorescent bulb, or CFL. Energy from the Variac excites the atomic gas inside, which emits light that is noticeably cooler than that emitted by the heated filament. By contrast, the light emitted by the gas in a compact fluorescent bulb shows well-defined peaks rather than the broad spectrum of light emitted by the hot filament in an incandescent bulb. Superimposed on the previous graph is the spectrum of the light emitted by excited mercury vapor. The alignment of the peaks at about 530 nanometers is evidence for the presence of mercury vapor in compact fluorescent bulbs. This peak at about 612 nanometers is the light emitted by the phosphor coating the inside of the CFL. This phosphor coating is used to make the light from the CFL appear warmer. It turns out that all elements emit light of only specific wavelengths when excited by a hot flame or by electrical current. The Thomson model of the atom, with its electrons embedded in a sphere of positive charge, was completely inadequate to explain the bright line spectra observed from heated atomic gases. A new model is needed.